Hello everyone, welcome to this video continuing to look at integration by partial fractions. So if you remember where we got to so far, we have an algorithm that helps us write our rational function in terms of simpler terms. And there are several steps. So step one we started with, we had to make sure the thing we're trying to integrate is proper, meaning the degree on the top is less than the degree on the bottom. If not, we have to use long division to make it proper. Then step two, we have to factorize the bottom as much as possible, so into linear terms and irreducible quadratic terms. And then step three, we have to write out the partial fractions decomposition and solve for the constants and finally integrate. And there are several cases depending on what the factorization of the denominator looks like. So in case one, we saw that in case one, there are only linear terms and none of them is repeated, meaning that none of them is a multiple of any other. So now we're going to look at case two, and then later there'll be case three and case four. So let's get started with case two. So we're supposing that step one and step two are already complete. So step one, meaning that the rational function we're trying to integrate is proper. Step two, meaning the bottom is completely factored. And now in case two, we're going to assume that there are only linear terms, but possibly some of them are repeated. So case two is when the denominator contains a repeated linear factor, ax plus b to some power r. So why do we have the power? So for instance, if we had, say, x plus 1 times x plus 1, if x plus 1 was repeated, let's say, then we could write x plus 1 times x plus 1 as x plus 1 squared. So if we have a repeated linear factor, we can always write it as linear factor to the power r. Okay, and in this case, we get kind of something similar to as we had in case one. In case one, we had a constant term divided by each of the linear term. But now if the linear term is repeated, we're going to have constant term divided by some power of the linear term. And we're going to go all the way from power 1 up to power r. So what do we mean? For example, here, if we had a linear term to the power r, so ax plus b to the power r, we're going to start off with a constant divided by x plus b, and then a constant divided by x plus b squared, and then so on for every power going up to r. So constant divided by x plus b to the r. So we don't just have constant over ax plus b, and we don't just have constant divided by x plus b to the power r. We have constant divided by x plus b for all the powers up to and including r. So for instance, if we had, say, x cubed plus 10x over x plus 1 times x plus 2 squared times x plus 3 cubed. Okay, this fits nicely into case 1 and case 2. Right, it's proper already. The degree of the bottom is 1 plus 2 plus 3, so 6, which is bigger than the degree of the top, which is 3. So it's proper. The bottom is fully factorized because there are only linear terms. And okay, there is a case 1 term, x plus 1. There are case 2 terms, x plus 2 squared, x plus 3 cubed. So for each of those bottom terms, we have to write out the correct factor. So x plus 1 is not repeated. It's just like case 1, we have constant over x plus 1. And then the x plus 2 squared is repeated twice. So we have to have constant divided by x plus 2 plus constant divided by x plus 2 squared. And then the x plus 3 cubed is repeated 3 times. So we have to have constant over x plus 3 plus constant over x plus 3 squared plus constant over x plus 3 cubed. Okay, so this will be the partial fractions form. In theory, you could multiply out and try to plug in values of x's and solve for these 6 constants. But in practice, we're not going to do examples that involve 6 constants we have to solve for. It would just be too cumbersome. But this is at least the idea of what the partial fractions term should be. Okay, so let's do some actual examples where we can compute things. So let's look at, for instance, the integral of x to the 4 minus 2x squared plus 4x plus 1 over x cubed minus x squared minus x plus 1. So it looks pretty complicated, but that's why we have an algorithm, just a sequence of steps we can follow. So let's try to do that. So step one, we look at the numerator. The degree of the numerator is 4, which is bigger than or equal to the degree of the denominator, which is 3. So this is not proper. So in step one, we have to start with long division and make it proper. And I'm going to skip over the long division here. It's kind of tedious. There's some algebra. We can do some examples in class if people have trouble with long division. But if you do the long division, this will come out as x plus 1 plus 4x over x cubed minus x squared minus x plus 1. So we're going to have to integrate this right side instead because this is easier to deal with. So for now, we're going to have to work on this fraction 4x over x cubed minus x squared minus x plus 1. But when we actually finish with the algebra and we get to do the integration, it's important to remember that this x plus 1 was there from before, that we still have to integrate this x plus 1. Okay, so let's try to rewrite this 4x over x cubed minus x squared minus x plus 1 and try to make it simpler so we can actually do the integration. And step 2, remember, was to factorize the denominator as much as possible into linear terms and irreducible quadratic terms. So we have to see how to factorize this. And it looks pretty complicated, and indeed it is pretty complicated. But remember, one thing we said is that if we plug in a number and the polynomial is 0, then x minus that number has to be a factor. So, and we can try plugging in, say, easy numbers like 0, 1, minus 1, 2, minus 2. So if you plug in here x equals 1 on our polynomial, you're going to get 1 minus 1 minus 1 plus 1, which is going to be 0. So from that, it turns out x minus 1 is going to be a factor. So we know already that x minus 1 is a factor. And then we can just try to guess what is in the what is the remaining factor if we pull out that x minus 1. So for instance, if we know that x minus 1 is a factor and we have to write something here, we started with a degree 3 polynomial, we're pulling out an x minus 1, so we have to have left a degree 2 polynomial. We want to write something so that when we multiply by x, we get x cubed. Okay, x squared would be reasonable. And then we need something that when we multiply by minus 1, we get plus 1 to get the constants to line up. So minus 1 is going to have to be the constant. And then we could try to figure out what are the possible x's. But actually, if you check by multiplying out here, x squared minus 1 times x minus 1 is actually equal to the thing we started with. So there are no x terms we need to consider. So if you're stuck trying to factorize something, try to plug in different numbers and see if you can see one of the factors straight away. For instance, x equals minus 1 would also work. Okay, but now that we have it to x squared minus 1, x squared minus 1 is easy to factorize, that x plus 1 times x minus 1. So we have x minus 1 times x plus 1 times x minus 1. Okay, x minus 1 is repeated, so we can write this as x plus 1 times x minus 1 squared. So now we've finished step 2, right? We've factorized the denominator as much as possible into linear terms and potentially irreducible quadratic terms, but they're not in this question, so we don't need to worry about those. And now step 3 is to write out the partial fractions form using what we talked about with case 1 and case 2. So the partial fractions form is going to be, of the thing we're trying to write, is, okay, for the x plus 1 term, that's a case 1 term, we just have constant divided by x plus 1. And then for the x minus 1 squared term, it's case 2, so we have to have constant over x minus 1 plus constant divided by x minus 1 squared. So remember, it's not just constant of x minus 1 or constant over x minus 1 squared. We need all of the powers up to 1, including the highest power. Okay, so we have to find a and b and c. So let's try to do that. It's an algebraic step. Since we don't like fractions, we want to get rid of the fractions. So let's multiply by x plus 1 times x minus 1 squared to both sides. If we do that, the left side is going to become 4x. And the right side is going to become, so the x plus 1 is going to cancel with the x plus 1 on the bottom. We have a times x minus 1 squared. We're multiplying by x plus 1 times x minus 1 squared. One of the x minus 1s is going to cancel out the b. So we have b x plus 1 times x minus 1. And then we're multiplying by x plus 1, x minus 1 squared. Where we cancel the x minus 1 squared, we're just left with c times x plus 1. And now, as before, we have two options. We can either multiply everything out and equate coefficients, or we can substitute different values of x. And I think substituting is, for me, at least easier. Let's try to pick good values of x to plug in. For instance, we see that some of the terms are going to disappear if we sub in x equals 1, and if we sub in x equals minus 1. So let's start with those. So if we plug in x equals 1, we get on the left side 4. And then on the right side, plugging in 1, we get 0, and we get 0, and we get 2c. So we have 4 equals 2c. So c has to be equal to 2. And next we said that subbing in x equals minus 1 will be good to make some terms disappear, so let's do that. If we sub in x equals minus 1, we get minus 4 on the left. And then we have a times minus 2 squared, which is 4, so we get 4a. And then we get 0, and we get 0. So minus 4 equals 4a, so a equals minus 1. And then we might want to look for another x value that makes some terms 0, but there isn't one. So x terms only become 0 at 1. The terms on the right only become 0 at 1 and minus 1. So there isn't really a natural choice of what x value to sub in. This is different to when we were in case 1. Case 1, there were no squares. There were always different factors. You could always find enough x values that make things 0. In this case, now we just have to pick an x value to substitute in. Since we have 3 unknowns, we need to substitute 3 x values. There isn't a natural one, so try to choose one that makes the calculation easier. For instance, I like to sub in x equals 0 if I haven't used it already. Just substitute in some small value of x. You'll get the same answer in the end, but try to substitute something that makes your calculation easy. And it has to be one that you haven't already substituted. So let's go ahead and plug in x equals 0. If we plug in x equals 0, on the left we get 0. 4 times 0 is 0. On the right we are going to get 0 minus 1 squared. So minus 1 squared, that's 1. So we get a. Subbing in 0, we get minus 1 times b. So we have minus b. Then we have c times 1, so we have plus c. So we have 0 equals a minus b plus c. But fortunately, we already calculated a and we already calculated c. So if we substitute in those values of a and c, we get 0 is minus 1 minus b plus 2. Okay, so b has to be equal to 1 for this equation to make sense, right? This is minus 1 plus 2 is minus 1. We pull the b of, minus 1 plus 2 is plus 1. So we have a plus 1 constant on the right-hand side. We pull the b over, we get b is equal to plus 1. So we managed to find a and b and c by subbing in values of x. Okay, so now let's remember what we had to integrate. We had x plus 1, which was there from the long division beforehand, so we have to remember to integrate that. And then we had these partial fractions terms, and I just replaced the a and the b and c by whatever they were supposed to be. And now we can integrate this because it's just a sum of simpler terms, and we can just integrate term by term with a sum. So for instance, the first two terms, we can use the power rule. We get a half x squared plus x. Then we are going to get, for 1 over x plus 1, the integral is L in absolute value x plus 1. For instance, you could do u equals x plus 1. For 1 over x minus 1, the integral is L in absolute value x minus 1. For instance, you could do u equals x minus 1. And then 2 over x minus 1 squared, this is 2 times x minus 1 to the power of minus 2. The integral is going to be minus 2x minus 1 to the power of minus 1. Why, for instance, if you did u equals x minus 1 on this bottom term, you would end up with 2 divided by u squared. That's 2u to the minus 2. Okay, so you can easily use the power rule. So these terms are easy to integrate just by making a substitution or thinking about it as a reverse of the chain rule, depending on how comfortable you are. Okay, so that's everything for step 2. So step 2 was when we have repeated linear terms. For instance, if we have ax plus b to the r, then in partial fractions, we have to have constant divided by ax plus b, constant over ax plus b squared, up to constant divided by ax plus b to whatever is the highest power. And then everything after that works pretty much the same as before. Okay, thanks everyone. See you next time.